Okay, so what we're going to do is we're looking at how we can find all roots of expressions or polynomials that have complex roots. Now, I mentioned the word root, I mentioned the word zero. Basically, if we're talking about either an equation or a polynomial, I'm going to call them roots. If I'm talking about an expression, I'm going to call them zeros. You can use the words interchangeably, it doesn't really matter. Now, if we have a polynomial with complex roots, what we discover is that the complex roots always come in complex conjugate pairs. So suppose we have this polynomial here, ax squared plus bx plus c. If we know that this guy has complex roots, then one root might be this, and if we know one root, we know that the other root is going to be the conjugate. Does that make sense? Wonderful. So if we turn our attention to number one, if an expression has three roots, x equals 0 and x equals 3 plus 2i, what is the final root to this expression and why? X equals 3 minus 2i. If 3 plus 2i is a root, whoops, then the conjugate of 3 plus 2i, which is 3 minus 2i, is also a root. If the question was state, then you could just write that. Don't have to write a story. Is that cool? Reasonable? Okay, so let's do something a little bit trickier. Find the expression with a root at x equals 2 minus 4i. X equals 2 minus 4i. Our root is going to be here.
2 plus 4i.
Yeah, so if we know that one of the roots is complex, then it must have how many roots at least?
2 roots.
2 roots. And if we know that one of the complex roots is 2 minus 4i, then the other root is?
2 plus 4i?
Yeah.
Ah.
Whoops. So we know the second root. Now the next question is, how can we find the expression? Now this leans into your last semester's work. Do you guys remember sum and product?
Yes.
Okay. The sum is a little bit strange. The sum can be written as negative alpha plus beta, where alpha and beta are these guys here and here. So this is alpha, this is beta. Now on the other hand, your product is going to be alpha times beta. In the book, it says the sum is alpha plus beta. It doesn't put the negative there. I'll explain after if you want to know why I do that. Now, putting this together, the sum is going to be 2 minus 4i plus 2 plus 4i. The complex components cancel, the imaginary parts cancel out. The real parts get negated. So your sum is going to be negative 4. For your product, that is going to be a difference of 2 squares situation. you're going to get 2 squared, take 4i squared. That's 4. This turns into a plus because of the I in there. This turns into 16, so you get 20. And now, piecing this all together, it's going to be something like x squared plus negative alpha plus beta x plus the alpha beta. This is actually a double negative, but you can write it as plus. So when we actually sub the values in, we're going to get x squared take 4x plus 20. And here's your polynomial. However, I've left one important thing off. I always forget this thing, but not today. Hey, there's always a dilation factor at the front unless you know specific values. Because you can have infinitely many polynomials or relations or functions that have these roots, but they can be dilated. So we say a is a real number that cannot be equal to 0. Does that make sense, guys?
Yeah.
Okay. I could go through another one, but I think it might be more beneficial to get you guys jumping straight into it, and I will support where support is necessary. We're working on learning intention 6 today, no 7, complex zeros and roots. You'll have to update your OneNote because it's changed overnight. It's 7G.1 to begin with. It's only small. If you want, you can have a look at the notes in the book. They do things a little bit differently. Either way is fine. Alright, so it's 7G.1. We're interested in, I believe, B, D, and G to begin with. So all we're doing here is we're finding the quadratic equations with real coefficients and roots. So we're applying this knowledge here for question 1. Then for question 2, find the exact values of A and B. So what you're going to do is you're going to build your polynomial that looks like this. Then you're going to play a game of matchy-matchy. So this will be, the polynomial you'll build is on the left-hand side of the equal sign. The polynomial on the right is what's written here. You play matchy-matchy. So the coefficient in front of x squared will be your A. The coefficient in front of the linear term x will simply be your B. And the the constant term at the end will be your product. I'll put an example on the board when you get up to it. There's not a whole lot to do there. After that, in 7G.2, this is all algebraic reasoning. I wouldn't say it's particularly important for the guys who are doing methods next year, but it would make your algebra exceptionally good if you can figure these things out. I have the work solutions, I can upload them. I just have to fix up question 8. I made a mistake on it. Seem okay? Yeah. Alright, this is pretty tricky stuff, guys. Don't let the lack of lines on the board of working out deceive you. It is a bit tricky for where we're at. So don't get discouraged if you're stuck, just ask for help.